The phase diagram for water represents the solution to the Clausius-Clapeyron equation, showing the equilibrium pressure, ES, for a given temperature between different phases. There are 4 lines indicated on this diagram, and all of them converge at the triple point, where all 3 phases are in equilibrium. There's an evaporation curve, which is the equilibrium between water and vapour, that's exponential in shape. There's a continuation of that curve into regions below 0 degrees Celsius, and we'll explore what that means in a minute. There's the sublimation curve, which is also exponential in shape between ice and vapour. And then there's the sharply sloped and negatively sloped melting curve between ice and water. And right at the top is the critical point, which we'll talk about in a minute. So the triple point O is where all 3 phases are in equilibrium, and this occurs at 273.16 Kelvin, or 0.01 degrees Celsius, and at a pressure of 6.112 hectopascals. The curve AO, which, remember, extends below freezing, represents equilibrium between supercooled water and water vapour. So we don't always assume that simply because liquid water reaches a temperature of 0 degrees or cooler, that it automatically freezes, and so we can have that equilibrium between water vapour and supercooled liquid water. The curve BO represents equilibrium between ice and water vapour. So deposition, sublimation, equilibrium curve. The curve CO represents equilibrium between water, vapour and liquid, and it terminates at C. That's the critical point, beyond which there is no phase discontinuity between vapour and liquid. That occurs at 647 degrees Kelvin and a rather large pressure, 221,000 hectopascals. The curve DO represents equilibrium between liquid water and ice, and as discussed in the lecture on the Clausius-Clapeyron equation, is steeply and negatively sloped. Ice saturation vapor pressure, ESI in hectopascals, is the partial pressure at a given fixed temperature of water vapor when it is in equilibrium with a plane surface of ice water, that is supercooled liquid water. And you can see that's along that dashed line that extends from the evaporation curve into temperatures below 0. So there's an equilibrium along that curve between vapor and ice. And for a given fixed temperature, ES is greater than ESI. So that's the ice saturation vapor pressure. No, wrong way. Finally, there's the frost point temperature, TF. And that's the temperature to which a given air parcel must be cooled at constant pressure and constant water vapor content in order for saturation to occur with respect to a plane surface of ice. So E is equal to ESI as a function of the frost point. And since there's a one-to-one, ESI is a one-to-one function of T, you can invert that and get the frost temperature. TF is only defined for temperatures below 0 degrees Celsius, and when this condition is satisfied, the frost temperature is always greater than the dew point temperature.